Good afternoon, ladies and gentlemen, and welcome to another session of Stop, Look, Listen, and Learn. Today we're going to be talking about Jensen's inequality. I received a lot of questions about this, and it can be somewhat complicated and confusing. So what I thought I'd do is go through a simple example to try and illustrate exactly what that means and why it is important. So let's start off by looking at a simple example. Let's say we have a call option, and we'll just draw this with a strike price of 100, and let's say that the price at time t can go up to 150, or it could go down to 50. So that's what the price could be at the end of 1 year. And we're going to say it is equally likely that it can go up to 150 or down to 50. And let's just draw the payoff of the call option, right? So this would be a loan call option. So the payoff function would be equal to, so we say f of s, we're going to call that the payoff function. We're going to say that's going to be equal to the maximum of st minus the strike price of 100 or 0, whichever is the greatest at the end of the 1 year period. So now with that in mind, let's look at what the expected price of the stock will be 1 year from now. So we said there is an equally likely chance that the price can move from 100 down to 50, or from 100 up to 150. So let's look at what the expected value of ST would be. So that would be equal to 0.5 times 50 plus 0.5 times 150. Because remember, the expectation operator just simply takes a weighted average of the random variable. So that's going to be equal to 0.5 of 50 is, what is that, 25, and 0.5 of 150 is 75, 75, and so that gives us an expected value of 100. That's the expected price of the stock 1 year from now, right? So let's box this, okay? Now, what we want to do is plug this expected price of the stock into this payoff formula and see what we get. So coming over here, we have the payoff formula, ST is equal to the max of ST minus 100, which is the strike price, or 0, whichever is greater. Now we just determined that the expected price of S of t is 100, so we're going to have the function evaluated at 100, which is going to be the maximum of 100 minus 100, or 0. So what that means is that the function evaluated at 100 is going to be 100 minus 100 is 0, and you compare that to 0, so they're both 0. So that means that the expected price of the stock 1 year from now is expected to be exactly what the strike price is, which means that the option would expire out of the money. So that is, we'll box this. This is what we refer to as the value of the function at the expected price. Now what we want to do is look at the expected value of the function based on the different values that the stock price can take. And then we're going to weight those different values of the function by the probability of the stock price actually achieving that price. So here's what we mean by that. So now we're going to look at the expected value of the function, right? And that's going to be, so there's a 50% chance that it can go down to 50. So it's going to be 0.5 times, we'll just put this here, the maximum of, what is that going to be, 50 minus 100, or 0, plus 0.5 times the maximum of 150 minus 100, or 0, right? So as you can see here, we're getting two values for the function. The first value is going to be 50 minus 100 is minus 50. Compare that to 0 and pick the greater of the two. 0 is greater than minus 50, so this is going to be 0.5 times 0 plus 150 minus 100 is 50. Compare that to 0. 50 is greater than 100, so we're going to pick the greater of the two, which is 50. So that's going to be 0.5 times 50, and that's 0, and then that's 25. So what you can see is that the expected value of the function is equal to 25. Now, what Jensen's inequality says is this. It says that when you have a concave function, now, if we draw this here, I'm sorry, a convex function. A convex function would slope up like that. And a concave function would slope down like that. And you can think of this as walking into the cave. Concave, walking into the cave, function slopes down. Convex, the function slopes up. So what Jensen's inequality says is that if you have a convex function, then what's going to happen is that the expected value of the function based on all the values that the random variable can take is going to be greater than or equal to the expected value of the function. Let me just rewrite this. It's going to be greater than the function evaluated at the expected value, right? So essentially what this is saying is you get multiple values for the function based on the values that this random variable t can take. So for example, if t can take, in this case, two values, 50 and 150, you figure out what the value of the function is when s of t is 50, and then you weight it by the probability of s of t being 50. Then you add to that the value of the function when s of t is 150, and you weight that value by the probability of s of t being 150, and you sum those, and you get the expected value of the function of that random variable. Whereas here, what you do is you determine what the expected value of the random variable is, and that's what we did here. It was a 50% chance that the random variable s of t would end up at 50, and there was a 50% chance that it would end up at 150, so you take the weighted average, and you found that to be 100. And then you take that expected value and you find the value of the function evaluated at the expected value of the random variable. And as we can see, the value of the function evaluated at 100, which is the expected value of the variable, was equal to 0, but the expected value of the function was 25. And that's, in a nutshell, what Jensen's inequality says, right? And that's important because this is the one that we would utilize for option valuation, as we'll go through in later videos. Because if we use this one here, we would just say, okay, well, the expected value of the stock price a year from now is 100, plug that into the payoff formula, well, then the option has no value. And we know that that's not the case. So we would do it this way. We would use Jensen's inequality and we would get the expected value of the payoff function and to determine what the value of the option is. So hopefully that helps clear up some of the confusion around Jensen's inequality. Please drop some comments if you found this helpful, or if you have additional questions, and I'll try my best to respond to those questions. And don't forget to subscribe to our channel. Thanks, and have a great day.